All right, let's dive right into this explainer, where we're going to journey from the terrifying mysteries of deep space to the explosive birth of the universe's absolute most massive objects. You know, black holes are some of the most captivating things in the entire cosmos. I mean, they sound completely like science fiction, but they are very, very real. Today, we're going to break down exactly what they are, how they actually come into existence, and just how unfathomably huge they can get. So grab your virtual spacesuit because we are heading straight into the dark.
So to really wrap our heads around black holes, we first have to grasp their invisible, totally inescapable pulling power. Simply put, a black hole is a region in space where the pull of gravity is just so intense, so incredibly strong that absolutely nothing can break free. Think of it this way. If an elephant tried to escape, it couldn't. But honestly, it goes way beyond elephants. Nothing, not even light, can escape that gravitational grip. And because light can't bounce back to our eyes or our telescopes, black holes are completely invisible to us, which is exactly what makes them some of the most elusive objects we could ever try to study.
Now, the ultimate point of no return, that's known as the event horizon. You can kind of think of it as the black hole's surface, though to be clear, it's not a solid surface you could actually walk on. It's really a mathematical boundary. You see, the speed of light is the absolute speed limit of the cosmos. Once matter or radiation crosses this specific threshold, the velocity required to escape the gravity actually exceeds that cosmic speed limit, and since literally nothing can travel faster than light, anything that falls past the event horizon is trapped forever, no way out.
And because of this extreme gravity, a black hole's favorite meal is actually spaghetti. Yeah, really. If you were to somehow pass that event horizon, which, hey, don't panic, the chances of us ever falling into a black hole are basically zero, you would experience a terrifying but completely fascinating phenomenon known as spaghettification. Because gravity increases so sharply the closer you get to the center, the pull on your feet would be vastly stronger than the pull on your head. So you, or any object falling in, would literally be stretched out to extreme noodle-like lengths.
Section 1. How are they born?
Well, gravitational collapse is the primary engine of creation here. Most commonly, black holes are formed by stellar death. But we're not talking about just any star here. It has to be massive. We're talking 25 to 100 times bigger than our own sun. Throughout its whole life, a star is basically doing this crazy balancing act. The immense gravity pulling its mass inward is constantly counteracted by the outward pressure created by stellar nucleosynthesis, basically the burning of nuclear fuel in its core. But eventually, that fuel runs out. When it does, the temperature drops, the internal pressure just completely fails, and gravity takes total control. The star's outer layers are violently blown away in this massive explosion called a Type II supernova. Meanwhile, the leftover core just keeps collapsing under its own crushing weight, compressing all that massive material into a tiny, unimaginably dense space. And boom, just like that, a stellar mass black hole is born.
But this is where the physics get absolutely mind-bending. Have you ever heard of gravitational time dilation? Because of it, an outside observer, like us, watching through a telescope, actually never sees the final formation of the event horizon. Even though the collapse happens really quickly from the perspective of the falling star material, gravity literally warps time itself. To an outside observer, the infalling material would appear to slow down and just kind of halt right above the event horizon. The light emitted by that collapsing material takes increasingly longer to reach us, eventually being delayed by an infinite amount of time. So instead of a sudden pop into darkness, we just see the collapsing core become dimmer, increasingly redshifted, and then slowly just fade away into nothingness.
Moving right along to Section 2, the black hole family tree.
So looking at the sheer scale here, we start at the very top with primordial or mini black holes. Now, these are currently theoretical, but scientists think they might have swirled to life in the extreme density right after the Big Bang, ranging anywhere from a microscopic Planck mass up to 100,000 times the mass of our Sun. Next up, we have the stellar mass black holes we just talked about, forming from dying stars and typically sitting between 3 and 100 solar masses. Then there's the intermediate class, which perfectly bridges the gap. And finally, the big ones. Sitting at the centers of almost all large galaxies are the supermassive black holes, weighing in at hundreds of thousands to tens of billions of solar masses.
Now, what's totally fascinating here is that intermediate mass black holes were actually a huge question mark for a very long time. I mean, we knew about the small ones and we definitely knew about the giant ones, but the middleweights were just missing. That is, until May 21st, 2019. On that day, gravitational wave observatories named LIGO in the US and Virgo in Italy detected this super unusual signal dubbed GW190521. It was literally just 4 short wiggles that lasted less than a tenth of a second. But that tiny, tiny fraction of a second was enough to prove, for the very first time, the exact moment an intermediate mass black hole was birthed into the universe. It was a massive game changer for astronomy. Which naturally brings us to Section 3. Is our sun safe?
Okay, first off, deep breath. The good news is our sun is simply too small to ever become a black hole. It just doesn't have the mass required to trigger that catastrophic gravitational collapse. But its eventual fate isn't exactly great for us either. In about 5 billion years, our sun is going to run out of hydrogen fuel in its core. When it starts fusing heavier elements, it's going to expand massively into what we call a red giant. During this phase, its outer layers will push so far out into space that it will completely engulf the Earth. So, yeah, unfortunately making our planet totally uninhabitable. Fast forward another billion years, and the sun will shed those outer layers and collapse into a small, extremely dense remnant known as a white dwarf, glowing faintly from leftover heat. So, for sure, no black hole for us, but still a pretty dramatic fiery end.
All right, let's get into the heavy hitters. Section 4, the biggest cosmic monsters.
Let's start right in our own galactic backyard. 4 million solar masses. That is the size of Sagittarius A star, the supermassive black hole sitting right at the center of our very own Milky Way galaxy. It literally has a mass equal to 4 million of our suns packed into a single point, constantly slurping up gas and dust that creeps too close to the galactic center. But as massive as 4 million suns sounds, it is practically tiny compared to what's really out there.
Because there is a staggering leap in scale when we look further out into the deep cosmos. We completely leave the realm of supermassive and enter the realm of the ultramassive giants. Take Homburg 15A, located in a group of over 500 galaxies called Abell 85. It has an estimated mass of 40 billion times that of our Sun. And then you have the black hole at the center of the IC 1101 galaxy. Sitting roughly 320 million light-years away from us, scientists estimate this absolute titan contains anywhere from 40 to 100 billion solar masses. It's so far away that we can't even detect smaller stellar mass black holes near it. We literally have to look for massive ripples in spacetime just to understand its properties.
But wait, because the current undisputed heavyweight champion of the universe right now goes to a celestial object known as TON 618. This is a quasar, an extremely luminous jet of light right at the center of a distant galaxy. And hidden inside that blindingly bright light is an ultramassive black hole with a truly incomprehensible mass, 66 billion suns.
To put that into perspective, to truly wrap your head around what 66 billion solar masses looks like, just consider its sheer physical volume. Its diameter is estimated at 242 billion miles. That's 390 billion kilometers. Think about how huge our own solar system is, out to the planet Neptune. TON 618 is so incredibly vast, you could fit Neptune's entire orbit inside of it, more than 40 times over. It is a cosmic monster of truly terrifying proportions. So, we've journeyed from the inescapable physics of the event horizon all the way to the mind-numbing scale of ultramassive giants. But, like most things in space, the universe is just so incredibly vast and full of mysteries waiting to be uncovered. While TON 618 sits comfortably on the throne today, it definitely leaves us to wonder, just how massive can these cosmic monsters truly get? Is there an even larger, older black hole hiding in the deep dark of the early universe, just waiting to take the top spot? And more importantly, what's your favorite black hole that we covered today? Thank you so much for joining me on this explainer, and keep your eyes on the stars.